Hello everyone, I am Bharani V, pursuing my Masters in Physics at RAE Mysore. In this session, I'll be discussing about CHOLESTERICS, a distorted form of the nematic phase. So in this session, I'll be discussing about what is liquid crystal, its classification and the types of classification based on the temperature at which it exists as well as the concentration of the solvents. Also, I'll be discussing about what is cholesterics and its properties like optical properties and the agents which affect the pitch of the cholesterics as well as few applications of cholesterics. So, we are all aware that there are three phases which are solid, liquid and gaseous phase. There are also other phases which are of intermediate kind. Out of one such intermediate phase is liquid crystal. So liquid crystals were basically discovered at 1888, and liquid crystals are state of matter that exhibits both solids as well as liquid properties. Now as you see here, this is the molecular arrangement of solid where it is of long range order. It possesses an ordered molecular arrangement. When such solids are heated, when the temperature is raised, they undergo deformation, and the intermediate state between this solid and liquid is liquid crystal state. Here, this intermediate phase possesses an ordered molecular arrangement like solids to some extent. As you see here, it is not completely disoriented, it is still ordered, but they have mobility characteristics like liquid phase. Thus, they are known as liquid crystals. The liquid crystals will have mechanical properties and symmetry properties intermediate in between those liquids and solids. And these liquid crystals play a crucial role in various technological aspects including displays, sensors and optical devices, which will be discussed later. So now I'll be discussing about the classification of liquid crystals. So liquid crystals can be organized into thermotropic, that is temperature dependent, and as well as lyotropic, which is concentration dependent. And in this session, we are concerned about cholesteric, which falls under the thermotropic category. So as you see here, thermotropic crystal liquids are a type of liquid crystals that exhibit change in their molecular order and physical properties in response to changes in the temperature. So as you see here, based on the temperature, we obtain three phases which are nematic phase, smetic phase and cholesteric phase. Out of which smetic phase is the phase which is obtained at the lowest temperature. And these smetic phases, as you observe, they have molecules arranged in layers. And they have a long range positional order within each layer as you observe. So thus these layers can slide apart each other, which is similar to soap. That's where this name has been derived from. Moving on to nematic phase. The nematic liquid crystals have their molecules aligned in a specific direction, which is parallel to each other. But as you can see here, they possess no long range positional order, as you observe here. Moving on to the concept of director. Director is the overall preferred direction of that particular phase. As you observe here, in case of a symmetric phase, the director is vertical in direction. But moving on to the nematic phase, here also the overall preferred direction is vertical, which is parallel to the molecule. And there is this third phase, which is cholesteric phase, which we are interested upon. Talking about the name cholesteric liquid crystal comes from the Greek word cholesterol. So it was initially observed that the liquid crystals exhibited similar optical properties to those of that found in the cholesterol esters. And also when viewed under a microscope, these liquid crystal displayed a colorful patterns which is similar to the way the cholesterol molecules arrange themselves. So therefore this name cholesteric was basically adopted to reflect their visual similarity to the cholesterol arrangement. So thus they were named as cholesterics. Cholesteric liquid crystals. These type of crystals or phases are also known as chiral nematic phase or twisted nematic phase. Only chiral molecules can give rise to this phase. I hope you are all aware of what is a chiral molecule. Chiral molecules are those that have no internal plane of symmetry. So thus chiral nematic phase exhibits chirality, which is known as handedness. So basically, if we dissolve a nematic liquid with a molecule that is chiral in nature, we observe that the structure from nematic phase undergoes helical distortion. Okay, so presence of orientational order but no positional order. So from this figure, we can see that within each plane of that molecule, we observe orientational order, but there is no positional order, which is almost similar to the case of nematics where we observe positional order, where we observe no positional order, but we do observe orientational order. Thus, they are given the name twisted nematic phase. It also has unique properties because of this helical distorted structure, which we'll be briefing out later in this session. So basically, this cholesteric phase exhibits twisting of the molecules perpendicular to the director with its molecular axis parallel to the director. So unlike the case of nematics and smetic, where the director direction, where as I have mentioned here, director is nothing but the overall preferred direction. So here as we see in case of nematics and smetic, the director direction is vertical. But unlike them, in case of cholesterics, each plane has a preferred direction. For instance, this first plane, which is at the base, has a director direction like this, whereas the corresponding next plane will have a director direction like this, and so on. So basically, we observe that the molecules are being twisted perpendicular to the direction of the director. And it was also observed that only racemic systems, only non-racemic systems can form cholesteric phase. I hope you are all aware of what a non-racemic system is. So it is an unequal mixture of two types of enantiomers, again where chirality comes into play. Moving on to the optical properties of cholesteric phase. As we know that the cholesteric medium is not exactly an isotropic medium, it was experimentally observed that it always shows Bragg's reflection. Okay, so for that, let us consider a planar texture which is enclosing an cholesteric medium as you observe here, and this has a left helix pattern. The cholesteric medium has a left helix pattern. And let us consider cases where we observe incident of two different light patterns. One is right circular pattern and another one, see here as you observe, is the left circular pattern incident light. The first case to be noted is that the reflected light is always circularly polarized. As you see here, we have two patterns of light incidenting the planar texture. It is always given that found that the incident wave components for which the instantaneous electric pattern is identical to the cholesteric helix, they get strongly reflected. As you see here in the case C, when the incident light has a left circular pattern similar to the left circular pattern of the cholesteric medium enclosed in the planar texture, we observe strong reflection of that light. So D, which you observe here, is the reflection of C. Then there are other components which are getting strongly transmitted as you observe here, where the incidence of a right circular pattern light is completely transmitted by the planar texture, which is having an pattern which is opposite to the incident one. In such cases, we observe strong transmittance of that light. So basically, the optical property of a cholesteric phase or a cholesteric medium is imparted due to its helical structure. Moving on to the next optical property, which is selective reflection. So these cholesteric phase was also known as twisted nematics, as mentioned earlier, because as you consider each plane, in each plane you observe a long range order orientation, as you see here, but there is no positional order. So because of this reason, they were named to be as twisted nematics. What about the orientation in each phase? As you see here, in the first layer, the molecules are oriented in a direction perpendicular to that particular plane, as you observe here. Whereas the adjacent plane, which is above that, has molecules which are oriented with certain direction with respect to the plane, and so on. And as you see the third layer, you observe that the molecules are oriented parallel to the plane of that particular phase. And the direction mentioned here is the overall preferred direction of the molecules present in that particular plane. Therefore, this is the director's direction. As you observe here, the director is in an helical direction. It is moving in a helical direction as you move across each planes. Therefore, we state that they have an helical distortion or helical pattern. Moving on to the concept of pitch. So pitch is basically the distance traveled by the uh, director in order to achieve the same direction of the director. As you observe here, the plane which is at the bottom has a director direction perpendicular to the plane. Similarly, we observe the same orientation of director after three particular planes. As you see, this plane and this plane has a director which is perpendicular to that corresponding plane. So the distance between these two planes is basically the pitch as it is marked here. So basically pitch is nothing but the distance taken from the director to rotate one full turn in a helix. That is known as pitch. As you observe here, in this case, this distance between these two planes corresponding to the same director direction is known as pitch. And this pitch of an cholesteric medium is said to lay between several thousand angstroms, which is said to be comparable with the range of wavelength of an visible light. So basically, the chiral pneumatic phase has a special ability to selectively reflect the light of wavelength, which is actually equal to the wavelength of the which is actually equal to the length of the pitch of this chiral pneumatic phase. So in other words, we can say that when a light falls on this chiral pneumatic phase, which is cholesteric phase, only that part of the light will be selectively reflected. Which part? The part of the light which has wavelength range which is almost equal to the pitch length. Only that part of the light is being selectively reflected by this cholesteric phase. Therefore, this is how the selective reflection mechanism is explained. So, as discussed earlier, selective reflection is one of the main characteristics of cholesteric phase, which was solely dependent on the pitch length. So there are various other factors which influence the pitch length and in turn which affects the selective reflection. Thus one such main factor which affects the pitch length is temperature. So as you see here, as temperature rises, we generally know that as temperature increases, the molecule tends to have great kinetic energy. So basically as T increases, T in the sense as the temperature increases, we see that the kinetic energy possessed by the molecule also increases. The kinetic energy K also increases. This in turn, what do we observe is that the molecules tend to make a greater angle. That is, the director tends to make a greater angle with the plane as compared to the earlier case. So in such case, we observe that the plane with molecules oriented similar to the initial one is attained at a very shorter distance. So in such case, the pitch length has been decreased. So basically what we observe is that the temperature increases, the pitch length decreases. So in such case, when a light incidence on such cholesteric phase, only that wavelength which is of the range of this particular pitch length will be reflected. So this is how temperature plays an vital role in case of selective reflection by the cholesteric phase. So as mentioned earlier, there are various other factors too which influence the pitch length. One such is temperature, as discussed earlier. Temperature varies inversely with the pitch length. Moving on to the next one, it is chemical composition. Chemical composition such as the molecular structure, the concentration and chirality also affects the pitch length. The chemical composition and the molecular geometry of the cholesteric molecules play a vital role in determining the pitch length. For example, molecules with large and more complex structure tends to have a long pitch. So similarly, concentration and chirality also plays a vital role. Moving on to the external field, which is one other reason which affects the pitch length. Electric or magnetic fields can be applied to cholesteric phase, which controls their pitch length, because this leads to changes in the structure as well as helical pitch and its optical properties in turn. Moving on to the next concept, which is textures and defects of cholesterics. There are various types, out of which one is focal conic, which is observed here, and cholesteric wedges. These images are TEM images, which is tunneling electron microscope images of the following. And there is other form of texture, which is fingerprint texture. As you observe here, this is how it is viewed under an tunneling electron microscope. And the cholesteric phase with defect appears to be this. As you see here, the pattern has been distorted. So this is basically defect in the fingerprint texture of the cholesteric phase. Moving on to the applications of cholesteric liquid crystals, they are widely used in the area of display technologies, which includes electronic paper, reflective displays, out of which few examples are smartwatches, outdoor signages, and e-readers. And the next application is sensors. They are widely used as temperature and humidity sensors, which works with the thermochromic materials and hygrometers. Moving on to the optical filters and security devices, they are used in 3D displays, camera lenses, and for optical communications, because they have a facility of tunable optical filters for controlling the polarization state of light. And as you see here, this is the recent advancement in the area of cholesteric liquid crystal. This is an color changing liquid crystal film which are used for advanced optical devices. Recently, the researchers have developed this, which is flexible and it is kind of an liquid crystal elastomer films. So that is all about cholesteric liquid crystal. Hope you liked it. Thank you.